In this instructional video, we're going to look at some basic concepts of complex numbers and some operations on complex numbers. Now, there was a Frenchman back in the late 17th century, early 18th century named René Descartes. He did not like the fact that you could not take the square root of a negative number, such as the square root of -1, because using the square root property, if you try to take the square root of both sides of this equation here, and we'll kind of do that like we did in earlier sections. When you try to take the square root of -1 on your calculator, it's not a real number. So it'll say non-real result or error or something like that. So what Descartes did is he defined the square root of -1 as the imaginary number I. And what he told his buddies, he's going, oui, if I could take the square root of this negative number, I could make particles travel along this metal line. And what that discovery led to, the discovery of complex numbers led to electricity. And a lot of people go, well, I'll never use this math for anything, but you reap the rewards. So this discovery, I equals the square root of -1, allowed us to develop electricity. So not a very big thing here, but without that, we wouldn't be, you wouldn't be listening to this, and I wouldn't be doing this right now. Now, numbers that are complex are in the form A plus BI. All right, so this is going to be called standard form, as we will see throughout here. And this is how you always write the answer to this, where A is the real part and B is the imaginary part. So we'll go ahead and put some examples here. We can put 6 minus 4i. Now, see, just because it's A plus BI form, in this case, A is the number 6, B is the number -4. Or you might have -2/3 minus 7i, where the A number, the real part, would be -2/3, and the B or imaginary part number would be -7. And here's a little chart versus real and complex numbers. Now, any real number can be written in complex number form as well. So let's just start here with the integers. And if we want to look at integers here, those are positive numbers, negative numbers. If you want to go ahead and define the set of integers here that you can count, it would look like this, forever and ever, both directions. So 1, 2, 3, 0, -1, so forth. Non-integers are just counting numbers that you can do on your hands and so forth. Rational numbers are fractions. We're going to get to some of those later on. That involves fractions, so we could put 2/3, -1/7. And of course, any fraction can be written as a decimal, so we could put -0.91 and so forth. There would be considered rational numbers. Irrational numbers are numbers that don't end or repeat, like our friend pi, or we could take some decimal that doesn't end, it looks really weird and nasty, and just say it goes on forever. All right, so all of these numbers encompass what's called the real numbers. All right, so you can kind of see that all of these boxes, all types of numbers that we can do on our calculator, lead to the real number system. And notice it says if it's a real number, B is 0, so it's really just the A part. All right, as we looked at in the previous example and slide there. Now, non-real numbers, when B is not 0, is when we have the I involved, or the square root of -1. And that all leads to complex numbers. So we can write all real numbers and imaginary numbers in complex form, A plus BI over here with the flow chart. All right, continuing. Two complex numbers are equal if both their real and imaginary parts are equal, so this kind of makes sense here. So if you know A and C are the same and B and D are the same, well, then those two complex numbers will be the same in the standard form. And this talks about a plus bi being called standard form for complex numbers. So when we now take the square root of a negative number, we can now write it as a complex or imaginary number in this form. So let's take a few here. So what this rule is saying, if we take the square root of something negative, it's going to be, since the square root of something negative gives us I, we can pull that out. So if we take some examples, let's just take some here. Let's say the square root of negative 25. We could break that up into the square root of 25 times the square root of negative 1, and we know that would give us 5i. Or we could take the square root of negative 49 and say that is 7i. Or we could take minus the square root of negative 9, and with that negative being out front, we're going to get to this rule. You always take the I out first before you do anything with complex numbers, and you can have negative i's as well. So that is what this rule is showing, that anytime you have the square root of something negative, it's coming out in as an I. So know that's what it is. All right, now here's some more examples that we talked about. So the square root of negative 16 for I, and they show that I coming out in blue there. It's pretty. The square root of negative 70. Now notice this one wasn't a nice square root. It did not simplify, but still, even though it's not simplifying, that I comes out because this could be rewritten as the square root of 70 times the square root of negative 1, and that square root of negative 1, the complex number I, led to the discovery of electricity. And then they'll even get more extravagant. They'll give you radicals that will simplify. So in this case, the square root of 48, we can break into the square root of 16 would be a nice perfect square number that goes into 48 times the square root of 3 times the square root of negative 1. So again, you can see what's going to happen here. That square root of negative 1 comes out as I. The square root of 16 comes out as 4. So you have a simplified radical complex number. All right, some operations here. Products or quotients with negative radicands are simplified by first rewriting the square root of something negative as I times the square root of a, and we've talked about this. Then the properties of real numbers are applied together with the fact that, let's think about this here, and Descartes really came up with a way to make his complex numbers like variables. So he said, wait a minute here, if I equals the square root of negative 1, what happens if I square both sides of this? Well, I squared becomes the number negative 1. So that was huge, and now we've got actually a complex number equal to a what? Real number. So remember, if I is the square root of negative 1, I squared is the number itself, negative 1. Now notice here, here's a caution. When working with negative radicands, use this definition before using any other rules. You must take that I out of the radical first. And if you don't, you can sometimes get in trouble. And here is, another caution here. So look out if you have, let's say, the square root of negative 4 times the square root of negative 9, because a lot of students might take this looking at the old rules for radicals here, and they might say, well, that's the square root of positive 36, which is 6. Okay, so it says this rule is valid only when C and D are not both negative. Now, look what happens here if you break these two apart using the product rule. If you take the square root of negative 4 times the square root of negative 9, well, the square root of negative 4 we just went over is 2i. The square root of negative 9 is 3i. Now, if you multiply those together and treat them like variables and so forth, you're going to get 6i squared. And remember, I squared is that wolf in sheep's clothing, negative 1, which gives you a negative 6. So be very careful on these, depending on, if one or both are positive versus negative. All right, so what do we mean by that? If you didn't get it last time, we're going to take the I out first in this example. And notice they do it in pretty blue here. So the square root of negative 7 is I times the square root of 7 times itself. And then whenever you have the square of a square root, that comes clean as this number. And then there's that I square is negative 1. So be careful. Take the I out first and you'll be fine. Another example, the example showing the same thing, except this one simplifies. We get the square root of 60, which it really doesn't show here very well, but the square root of 60, if you look at it, will be the square root of 4 times the square root of 15. And notice taking the I out first has that I square out here. And therefore our final answer is going to be negative 2 times the square root of 15. So operations on i's, and you can also divide them and so forth. Again, notice even when you divide them, take the i's out first. And in this case, I divided by itself cancels out, leaving you with the square root of 10. So be careful. Take that I out first and you'll be good. Same thing here. We've got taking the i's out here. The I... Oh, I'm sorry. Looks like a mistake in this graphic here, because notice the problem up here has a positive 24. And down here, somehow the graphic got changed. So we're going to make this a positive here. So you've got to watch these graphics every now and then, which means this I is no longer here. So we've got to watch these graphics here when you do this. So you're going to end up with just a single I in this problem, having fixed it, over the square root of 48 over the square root of 24. So you can simplify and divide square roots and get square roots, and you will get I times the square root of 2. So a little mistake on that one, but we caught it. And then they'll give you even nastier ones with fractions and so forth. So just simplifying radicals here. So we're just going to go ahead and take the square root of negative 128 and break it up into the square root of negative 64 times 2. The square root of negative 64 comes out as 8i. Now, are we done in this bottom down here? I don't think so, because remember, Descartes said you must write all of these answers in form a plus bi. So we're going to continue here and show you that you can factor out a 4 in the numerator here, which will give you, if you factor this out, negative 2 plus 2i times the square root of 2. And of course, you could check this by distributing. And then the 4's would cancel out, giving you this standard form, a plus bi. All right, so that is a quick review of complex numbers and introduction, and we're going to do all kinds of new things with them as we progress. Bob Young signing off.